that up. Okay, so Mark Thompson was due to speak here today. Unfortunately, he sends his apologies. I'm delighted to be speaking in place of Mark. And we were asked to talk about our vision for a quantum data center. This is it. This is my job done, right? This is an artist rendition of a compute site that we're planning to build. And what I'd like to do is spend the next 15 minutes or so telling you about our plans of how we're going to populate this site and how we plan to scale up and build a computer. But before I get into the details, I'd just like to thank all of my colleagues at PsiQuantum. I joined relatively recently, so the work that I'm going to talk to you about, I can't really take any credit of at all, and it's really all the hard work of my dear colleagues at PsiQuantum. So as we've heard today, there's very, very strong motivations as to why we want to build quantum computers. And there's key and exciting applications across all of these sectors. And this has motivated a huge amount of effort and expertise to build some of the most exquisite quantum experiments that we've seen today, really exquisite levels of control. And this is one of my favorite quantum devices. This is Google's machine. This is in Santa Barbara. Most of what we see here is technology to cool down their quantum processor so the machine cools down to about the temperature of deep space, and then it cools it down by another factor of 100 or so. And mounted at the bottom of this equipment is a chip that will fit into about the palm of your hand. It contains about 100 qubits. And it's an amazing device. It can unequivocally outperform supercomputing today for particular tasks. But when you look at the statements of CEOs of NVIDIA and Alphabet and IBM and Google, they all realize that we need about 1 million physical qubits to do something of commercial value. And what's been emerging in the community is that to achieve this, you need to build something that looks like a quantum data center. You need to modularize your system. And this has very much been the ethos of the company that I now work for since the very beginning of its founding. So yes, we need exceptional qubits, but we also need to be able to satisfy these other criteria that I've listed here. We need a clear pathway to manufacturing. We need all the cooling power requirements that we might need for our given architecture. We need to have connectivity, and we also need the control electronics. So I should briefly just mention we're a photonic quantum computing company, so we're encoding our qubits using single photons in one of two paths. We also use time bin encoding, which I'll show later on in a particular slide. But and then the kind of sketch of our architecture is given by this cartoon here. So you start out with this kind of messy arrangement of dots. Those are signifying the fact that the photons are not produced in all of the exact places that we want them to be. We use fast optical switching in what we call multiplexing to put those photons in the right place, and also to entangle the photons. And then we proceed with the rest of the calculation. So that's about as deep as I'm going to go into the architecture. I want to focus instead what's going to be going inside the site that I showed you earlier. So for realizing photonic quantum information, we identified that we could use a lot of the technology that's been developed by the telecommunications industry. So beam splitting networks, optical ring resonators, and so on. We can take those devices that have been developed by the telecommunications industry. Maybe we need to finesse their performance to meet our requirements, but we can put that into our architecture. And then there are some components that we've had to develop ourselves from scratch, which includes integrating superconducting single photon detectors. So that's a quantum device that sits in our architecture. And then we partner with a tier one semiconductor manufacturer to scale up fabricating these devices. We work with global foundries. We also have needed to develop a pathway to packaging at scale our devices optically and electronically. But then we also need to think about how we're going to provide all of the cooling that we need. So we've had to develop means for cooling down these components in a modular architecture. And this panel, almost on the right there, these are our what we call our side blades. These are inserts that then go into cabinets that are cryogenically cooled. So we've had to develop a new class of cryostat that can take lots of devices for greater efficiency of cooling. And then that's so that we can then connect all of these cabinets together in a modular architecture in something that starts to look like a data center. So I just want to take you through that slide that I've just shown you. So this is a $14 billion tier one fabrication facility. This is Global Foundries in upstate New York. And this is where our photonic devices are fabricated. We have colleagues from PsiQuantum who are embedded in this facility, fabricating devices for our machines. And what I would just also say is if you've got a smartphone on you or you've got a laptop in front of you doing your emails, chances are that you've got chips inside that computer that's been fabricated in this facility. So this is we've seen that this is key in order to scale up the photonic devices at the performance level that we require. Okay, and then you'll have to take my word from it because you can't recognize them, but these are some of our PsiQuantum colleagues who are embedded in Global Foundries. I think that's Pete Shadbot on the left there, but I don't know. Okay. And then what's also important, you don't want to just make the devices, you need to have a very high throughput of test and measurement to have rapid iteration of your development cycles. And these numbers this number at the top here is already slightly out of date, but we're well into the 8 digits of devices that we've tested. And we're keeping up a pace of about 500,000 room temperature tests per month and 50,000 cryogenic tests of devices per month. And we see this is key in order to keep pace with how we manufacture and how we develop our hardware. And all of this hard work has culminated in our publicly releasing information about our chipset, which we call Amiga, which is a platform that includes single photon sources, superconducting nanowire single photon detectors, and also the means with which to shield those detectors from any stray light that you don't want to get into your readout. Of course, passive optics, including beam splitters. We've also bus waveguide with a series of rings. That's sketching out our tuneless source, which is also fabrication tolerant. So we're very excited about this. This is a photon source that doesn't require any power. You don't need to tune it, and it can tolerate the kind of fabrication tolerances that we get in foundries. And we've also developed photon number resolving single photon detectors, and then also gigahertz switching technology using barium titanate. Okay, so this is just to show you some of the devices. Those that have worked with semiconductor devices might recognize some of the very high quality of some of these devices, looking at, for example, the smoothness of the walls of the various features. But I wanted to show you some actual physical devices, and this is what they look like at the very small scale. Of course, the devices perform well as well. So here's some example results of individual components. I won't dwell on these results for too long, but we can take the individual components and put them together to do, for example, single qubit generation and measurement on the same chip, and we get very high performance there. We've also got demonstrated very high performance in interconnecting chips and sending a qubit from one chip to another, and also 2 qubit operations as well. Again, combining these different components together into single chips. So we've always been a modular architecture company. So key for that is developing extremely low loss interconnects from one chip to another. And these are results demonstrating that we can achieve down to about 100 millidB loss from going from waveguide on chip into optical fiber, and we think this is key, and we're very happy with these results. And then also to just spend a bit of time on our detectors. So on the left, we've got the illustration of how the cartoon illustration about how a superconducting nanowire single photon detector would work. There would be a light field that's going in. There may be one, or there may be a few more than one photons going in, and then that gives you a click. We've developed how to arrange that so that we can get some information about the total number of photons in that state going into that light field. And then I mentioned the fast optical switching. This is key for our architecture. And this cartoon on the bottom right is kind of illustrating how you take those photons that are generated maybe in the wrong place, and how you route where they should go by combining a delay with a gigahertz switching optical switch. And this is something that we had to develop ourselves. We weren't happy with the capabilities out there, so we developed this machine. So this is the world's first 300 millimeter molecular beam epitaxy tool for fabricating barium titanate wafers. I showed you one of those wafers previously, and this is what we're using to do our fast optical switching. This is sitting in one of our sites at California. And that's a 64 by 64 BTO optical switch. That's what it looks like when it's diced up and put onto a PCB and electrically and optically packaged. And I mentioned, that we predominantly use path encoding. That is a photon that's in one waveguide or another to encode your 0 or 1 state. But we also use time encoding for doing interconnects. So we use this BTO switch to do a fast optical switch to convert space into time. And we've demonstrated at our Daresbury site sending single qubits from one chip to another over 250 meters. And we've seen very nice fidelities. And I should also stress that we've done nothing to the optical fiber itself. That's just going into a tunnel underneath all the roads and so on, going from one lab to another. And despite that kind of lack of stability on the actual fiber itself, we don't see any effects on the interconnect here. And the 250 meters is not by accident. This is the kind of size that upper bound of how far we might want to be connecting one cryo cabinet with another. So we think we've solved the interconnect problem for our architecture. So we can make as many chips as we could dream of, and we know how to connect those chips together. Can we cool them? And this is and can we cool them at scale? So I just want to spend a few minutes talking about this. So this is the STFC site in Daresbury, which is very close to Liverpool and Manchester, and we have a lab there that is accessing STFC's cryo plant. And so these are all the different ingredients of what's needed to cool down one of our prototypes for a new type of cryostat, which is sitting in the lab that's marked with the psi there. And this is the cryostat. We call it the PsiQube. So it's 10 watts of cooling power at 2.4 Kelvin. My colleague Tom's there is going to open the door for us to have a look inside. And then what we're doing is we're mounting several chips in sub-assemblies inside this cryostat, so we can run multiple experiments at the same time. So yeah, so we did that because the cooling power of commercially available chandeliers wasn't sufficient. So we needed to develop a new class of cryostat, and that was our first prototype. The next prototype is what we call the Mark 1. So we go from 10 watts of cooling power at 2.5 Kelvin in the PsiQube to about 30 watts of cooling power for the Mark 1. And if this works, this is the Mark 1 being installed in the Stanford Linear Accelerator, so we can access the cryo plant that's there. So you can see you need kind of lifting cranes that look a bit like the lifting crane that's out there. And I was asking my colleague and friend Jorge if we could get that one running, if we could be moving cryostats around. So so that's been delivered and installed, and it's under operation. And you'll see from the time tag on that video that that was last year. And then the next stage is the Mark II. So this is something that's being built in the UK right now. And this cryostat is designed so that we can test out our side blade inserts. So this has 50 watts of cooling power. You can see on one side, we've got 20 inserts. It's the same on the other side. And then this is an image of the inserts that we're developing. So basically on the back, that's the cold bit. That sits next to the cold plate at 2.5 Kelvin. And then that moves through to room temperature where it's interfacing with the outside world. Okay. So this is how we see scaling up increased cooling capacity for our architecture. And then the next phase will be to start to link these cryo cabinets together to build a larger system. And so where are we going to build these systems? Well, we've identified two sites, one in Brisbane and one in Chicago. And I'll give you, that's a close-up of the image I showed you right at the start. This is the plan of what the center in Brisbane will look like. So we've got our kind of compute hall in the middle here, and we've got infrastructure for a cryo plant, which is needed for giving the required cooling power needed. So I'll just finish with a quick overview, which I think gives a kind of fair sketch of what our company is doing. So we start with the wafers themselves, where we're developing the photonic devices. We dice up into chips. These chips have single photon generation and manipulation and detection. We've been developing how to modularize these in modular inserts that we then plan to put into cryo cabinets that we've been developing. And then this networks up with other cryo plants. And in a moment, we shall hopefully see a little sketch of what the site in Chicago is planned to look like as well. So there we go. That's our vision of how we're going to scale up and build a quantum computer. Thank you very much for your attention.